This video is about designing a simple active bandpass filter. It corresponds to the second part of section 24.4 of Applied Analog Electronics. To review from the previous video, we're talking about an active filter here. So we have an op-amp, and it's going to be in an inverting amplifier configuration. So VREF will come in the positive side, and we will have a capacitor and a resistor in series on the input, and a capacitor and resistor in parallel for the feedback. And we gave these names before, CI and RI for the input, CF and RF for the feedback. And let's do one thing to simplify the notation a bit. Let's say that we've got two time constants. Tau F is RFCF, and tau I is RICI. So it's just to avoid having to write RFCF and RICI all over the place. And we had previously derived the angular versions of the corner frequencies, omega low and omega high, to be 1 over tau I plus tau F, and 1 over tau I plus 1 over tau F. Okay, so let's look at some consequences of these corner frequencies. For one thing, we're interested in how far apart are the corner frequencies? How close together can we make them? Can we make a really narrow bandpass filter? And the answer is no, but let's see why. Well, if we look at the ratio of the frequencies, so omega high over omega low, which is the same as the ratio of the frequencies because the two pi's cancel, that's going to be 1 over tau I plus 1 over tau F times, inverting that, tau I plus tau F. All right, we can multiply this out. The tau I plus 1 over times 1 over tau I, and the tau F plus 1 over tau F. This is going to be 1 plus 1, or 2. And then the cross terms will be tau I over tau F plus tau F over tau I. So that's a ratio. Let's call it x, and 1 over that ratio, 1 over x. And x plus 1 over x is minimized when x is 1. So this thing's always going to be at least 4. And it's going to be minimized when the two time constants are the same. So that's telling us that the ratio of our two corner frequencies is going to be a ratio of at least 4. And that's the smallest we can possibly get it. That's if we make both time constants the same. If we make the time constants different, corner frequencies just move farther apart. And so we can't get a very narrow bandwidth out of this filter design. That's not to say that all active bandpass filters have a wide one, just that ones designed in this simple way do. There are other designs that involve multiple feedback and stuff that can get you narrower bandwidths if you need it, but that's a little bit beyond the scope of what we'll be doing in this class. Okay, what else can we do with this, these formulas for the omegas? Well, we could look at the product also. So omega low times omega high. Well, that's going to be 1 over tau I plus tau F times 1 over tau I plus 1 over tau F. And we could get this thing to have a common denominator, so it's leaving the omega low again. And this is then going to be tau F plus tau I over tau I tau F. But now we have the 1 over tau I plus tau F and the tau I plus tau F on top here. Those cancel. And we get that the product of them is just 1 over the product of the time constants. And that's really very nice. It allows us to do some easy ways to set omega low and omega high. For example, if the ratio of the two is very large, so we have a huge omega high and a tiny omega low, so we've got a wide bandpass filter, then we can say, well, one of these time constants is going to be big and one's going to be small. I mean, and we can pick it actually so that, say, tau f, we can make omega high be about 1 over tau f, and that's if tau I is really big. Well, if tau is really big compared to tau f, we get 1 over tau I for omega low and 1 over tau f for omega high. And this is an approximation that people often use when designing that. They just say, okay, I'll put my low corner frequency on this impedance, and I'll put my high corner frequency on this impedance, and I'm done. And that works pretty well if the corner frequencies are far apart, because you can approximate this thing very closely with that. The center is going to be in the right place. Everything's going to work just fine. But when you're trying to make a narrower bandpass filter, then the approximation doesn't work anymore. You're trying to make the thing where it's only a factor of 4 apart, then you've got tau I equal to tau f, and you can't make the approximation that one of these is big and one is small. They're the same. You get like here you'd have 1 over 2 times the time constant, and here you'd have 2 over the time constant. So it gets a little messier when you're trying to do a narrow bandpass. But let's take a look at another way of thinking about what is that narrow bandpass trying to get. What are we trying to do? What we're really trying to do is to find the two values of tau. So, we can think of it, we've got t minus tau 1 times t minus tau f equals 0. That's the two values of tau that we're trying to find. If we write this thing out, that's tau t squared minus tau I plus tau f times t plus tau I tau f equals 0. We can see what tau I tau f is, and we can see what the sum of tau I and tau f is. So this is just t squared minus 1 over omega low times t plus 1 over omega low omega high equals 0. That's just a quadratic formula in t. You can plug in the value of the corner frequency you want here, the value of the corner frequency you want here, or the product of the corner frequencies, and solve for t. For that matter, you can do it with a program like Wolfram Alpha. And so it then just becomes a matter of, if we've got two roots to this quadratic equation, one of them's tau f, one of them's tau I, which one's which? Well, it's generally easiest to work this one so that the larger tau value, the one that corresponds to the higher frequency, goes with the feedback, and the smaller tau value goes with the input. That turns out to give you the easiest control of the gain, and generally an easier way to think about it, because the simplification we did before, when the corners were really far apart and we just stuck one corner frequency here and one corner frequency here, that's the way we chose it. You could, in fact, have swapped those. Notice that the corner frequency equations here don't care which one's on the input and which one's on the feedback. The gain equation, though, the resistors and capacitors there did matter, because for the gain equation we had on top one resistor and the other capacitor. And so if you wanted to get a large gain, it does matter which way round you put the two time constants. Okay, this has been just sort of a generic view of how you go about solving for this thing. Set up this quadratic equation, solve for your two time constants. It might be good in another video to look at a worked example.